Hello everyone, welcome to topic 5.9, Steady-State Approximation. In this, you should be able to, by the end, identify the rate law for a reaction from a mechanism in which the first step is not rate limiting. So we've kept it very simple so far, where the first step limits the rate of the reaction. Well, if we go back to our chocolate analogy, where the second step, the cooling step, took 8 hours, right? It is not always the first step that limits how fast you can get something done. So we need to then look at how we can approximate rate laws if the rate determining step is not the first step. And so we're going to do that today. When the first step of a reaction is fast, not the slow step or rate determining step, we need to approximate the reaction rate through a process that College Board calls a steady-state approximation. A true steady-state approximation is a little more involved than this, but we're keeping it simple, guys. We first introduced this idea in 5.4 and said, hey, we're going to come back to it. Well, here we're coming back to it. The slowest step in the reaction determines the rate of the reaction, right? If the first step is slow, then the overall rate for the reaction will be based on the stoichiometry of the first elementary reaction. If the subsequent elementary reaction is slow, so not the first one, then you have to add all the reactants up to the slowest step and cancel any intermediates to determine the rate of reaction. We're going to go over how do we do that in a second. In cases where the slow step is not the first step of a reaction, when we write the rate law that is predicted by the rate determining step, so in this case like this one, right, when we write that rate law, it would be based on B and C, right? But B is an intermediate and cannot appear in the rate law, and so because it also does not appear in the overall reaction. So we have to express the concentration of the intermediate in terms of the reactants and substitute, and we're going to look at how do we do that. So first, if you look at the first step, the mechanism, the reaction is fast, which means B is formed as quickly and starts to accumulate. As the amount of B increases, some of the B reacts to form A, the reactants. This is called an equilibrium reaction because it goes both ways and is designated with a double-headed arrow. As long as the first step of the reaction is fast, there is always B available for the second step, so it doesn't limit how fast you can proceed. So the first step is not limiting, right? So you can focus on the second step if it is limiting. Since the second step is consumes B slowly, the amount of B intermediate remains fairly constant over the course of the reaction. When the rate of the forward reaction equals the rate of the reverse reaction, we say that this is at equilibrium, right? And so it's still reacting, but the rates are the same for going forward and reverse. So now looking at this, first we need to make sure that the mechanism is valid. To do that, we add the two equations together and cancel out intermediates. We see this overall reaction here, and so the observed rate is here, and it should kind of mirror. Since the second step is rate limiting, we can write the rate law for that step, which we did here. Okay. However, B is an intermediate, so we must substitute in for that. We need to switch it out so that it is not in the rate law by expressing the concentration of intermediate B in terms of the concentration of the reactants. We can do that using the first one here. Okay. So we know that the rate forward, because it's at equilibrium, the rate forward is equal to the reverse rate, right? At equilibrium. So we can write the rate law for the forward reaction, so A squared, K1 times A squared, and that is equal to the rate of the reverse reaction, which is K negative 1, because it's the first reaction, but it's going the other direction, times the concentration of B, not squared, just B. And when it's reversed, the products then become reactants. So we can do this with that. And since B is the intermediate that we need to get rid of in our initial rate law, so it's not that one, B is here, right? We're going to rearrange this expression by dividing by K negative 1 on both sides to get B by itself. Well, now we have B by itself, and so we can plug it in to our rate law expression here, and we do that because this is B. Okay? The great news is that we can now switch this K to K1 over K negative 1, right? These are all reaction constants. We can just say that that is K, the overall K. It doesn't matter that it's from separate reactions. It ends up working it out when we look at the initial concentrations and initial rate when we calculate K. So that is based off of experimental values. It doesn't matter if we simplify them from the elementary steps, because they do add, like, combine to give you an overall reaction constant. Okay, so now we can simplify that into a single K value here, and we see that this does indeed give us that observed rate law here. Okay, so let's practice that. So I do. The ozone naturally decomposes into oxygen according to the following reaction. The experimentally observed rate law for this reaction is as given. The reaction occurs in 2 steps. Which one is the rate limiting step? Okay, so the rate limiting step should mirror our rate law. Okay, but we can't verify that without checking. So we need to then check to see if this is our slow step. So if we put this one as slow, because usually equilibriums are not the slow step, but we can check, right? So we would say that rate of KO3O, right? If this was the slow step, is the other thing, is that it would be mirrored directly to this, but it's not. This does not, this rate law, which should be rate is equal to K times the concentration of O3. This does not match the experimentally determined rate law. So the true rate law is this one. If this is the slow step, this is the rate law we should get. It isn't. So that tells us that it must be the next one. Okay, it must be this one, the second one. So that means that we can then show that this agrees. So the rate law for the slow step would be as here. However, we cannot use it as written. So we go, because it has an intermediate, so we go to the first step and we write the rate law of the forward reaction, which is, and remember that for this, the rate forward, because it's at equilibrium, is equal to the rate of the reverse. And so we can write the rate law for the forward reaction, which is K1, my apologies, K1 times the concentration of O3, and that is equal to the rate of the reverse, which is K negative 1 times the concentration of O2 times the concentration of just oxygen. Now they don't have coefficients, so I don't have exponents, they're all 1. Now I need to get rid of the oxygen atom in my overall rate law expression, so I'm going to solve for this one. That means I'm going to divide both sides by K negative 1 times oxygen gas concentration. And so I should end up with my intermediate being equal to K1 times O3 over K negative 1 times O2. And so I can substitute this in for this oxygen. So it's like a systems of equation problem, but weirdly convoluted from, because it's chemistry. Why not? So rate is equal to K times O3 times what I get from my substitution. So K1 times O3 over K negative 1 times O2. So now I can simplify. My K's all become just K. So rate is equal to K. And then O3 times O3 is, my apologies, O3 squared divided by O2, because that's what's left on the bottom. And we can write that K a little bit better. right? And so this does indeed mirror the overall rate law that was given experimentally. So this does work, and it does match. Okay. Oh, no. Too zoomed in. Okay. So now let's look at the we do. The mechanism shown here is proposed for the reaction below. So we have 3 steps in this. Write a rate law that is consistent with the mechanism. So we start with the slow, and we write the rate law, and that's based off the reactants. So my initial, and I'm going to actually start up here because I don't have a lot of room. So my initial thought for the rate law is that it is equal to K times the concentration of B times the concentration of D. However, I have to substitute out any of the intermediates. Well, in this, D is an intermediate, so I need to substitute it out. I'm going to use this expression to do so. So when I do that, I would write that the rate of the forward, so K1 times A squared, is equal to K negative 1 times the concentration of B times the concentration of D. Actually, I have to substitute in for both of these, right? They're both intermediates. They are, or kind of both intermediates. They are both not reactants, and your rate law is always in terms of reactants. So if I rearrange this expression, right, to solve for B and D, I end up with the concentration of B and D. It's kind of like X and Y are present, and I'm just going to make this a little more simple for me, is equal to K1 times the concentration of A squared all over K negative 1. That means I can plug this in for all of this right here, and so I end up with rate is equal to K, technically this is K2 because it's for the second step, times K1 times A squared over K negative 1, and I know I can simplify my K's to just K, and then I bring down A squared, simplifying everything, and so my overall rate law should be this one. And it is consistent with the mechanisms because I showed through substitution how I can use the equilibrium expression to get there. Okay, so using this concept, you guys are going to do the same thing with the you-dos. Please work through it, check your work, and thank you for tuning in.